What the heck is a Ramachandran plot? Well, we're going to go through that today, but to start understanding what a Ramachandran plot is, we need to first understand what we think about when we think about protein structure. So, up on the top here, we have a protein. I'm going to zoom in here. Remember that NC-alpha carbonyl is going to be an important way that we distinguish direction in proteins. So nitrogen is always going to be blue. So in this case, we've got an NC-alpha carbonyl. So NC-alpha carbonyl, NC-alpha carbonyl. So we can see our direction here runs N to C. So let's go ahead and write that down here. This is the N terminus running to the C terminus in this protein. So a couple of things to note here when we look at our backbone. In general, we want to see a trans configuration of our backbone because that's going to give every atom the most room. So in general, we are going to see a trans configuration that we're going to have. So this is a trans configuration that's going to give everybody the most room. And that trans configuration is also going to allow us to alternate the sides that we put our big bulky side chains. Okay, so here we can see here's our R groups, our side chains, and they alternate on opposite sides of our peptide backbone. Okay, so even when you have small ones. So most peptides adopt what we call the trans conformation. So these are conformations. Configurations like L or D when we're talking about stereochemistry have to do with things that are only interconvertible by breaking bonds. These are conformations so that we can obtain them by rotating bonds. And so even though all of these bonds can be rotated about, okay, we're going to tend to see this trans conformation. Even though I used configuration, we're going to see this shape because it gives everybody the most room. So big picture here, when we talk about structure formation, it's a balance of energetics and sterics. And we're going to get to that on this slide. Okay, so to have these side chains alternate, just to kind of sum this up here, our side chains are going to alternate. And that's because of sterics. We're going to give everything as much room as possible. All right, so we've got this peptide backbone, and I want you to think about when you have this peptide backbone and then you've got your side chains alternating on every side. At the end of the day, I want you to think about this kind of like a charm bracelet, where the bracelet part is our peptide backbone and the charms that dangle down are our side chains. And I actually am going to refer to those side chains as dangles. Okay, not very scientific, but it's going to help us make sense out of all of this. Okay, so let's think about what it means to have structure formation. So we're going to get to this picture that's over on the right in a minute, which is the Ramachandran plot. But let's just fundamentally talk about what it means to have structure formation. So structure formation basically takes into account two things. It takes into account sterics, and sterics are important because we want to avoid things banging into one another. So avoid atoms banging into one another. Okay, and that's what we got to up on top. When we said here that we're going to have our side chains that are alternating on our peptide backbone, that gives everybody the most room possible. So structure formation is going to take into account sterics, but it also takes into account energetics. Okay, we ultimately want to optimize both entropy and enthalpy. So let's take these one at a time here. When we think about entropy, remember the phrase that I told you to think about with entropy was more molecules moving more. So more molecules moving more. So when we form structure, we actually have molecules moving less because we're freezing out molecular motion to have a specific structure. So entropy, when we form structures, is actually very unfavorable. So entropy is unfavorable with structure formation. Well, hopefully we remember from thermodynamics, we are not going to have a process happen if entropy and enthalpy are unfavorable. So already sort of predicting here, but it is the truth that when we think about enthalpy here, and we think about, right, this was more molecules moving more, we think about bonds and intermolecular forces when we think about enthalpy, that is going to be favorable when we think about structure formation. And so what we really have here when we form structure is what's referred to as an entropy enthalpy compensation. And that's very common in a lot of what we're going to see energetically. Not often are you going to have those win-win situations where entropy and enthalpy are both helping you. Oftentimes when we're doing things biochemically, we're making systems more ordered, and that's very unfavorable from an entropy situation, so it must be compensated for in some way by enthalpy. We're going to get to what those enthalpic compensations are in just a little while, but to highlight, what does this Ramachandran plot have to do with any of these? Well, the Ramachandran plot really has to do with the sterics piece. So we want to avoid atoms banging into one another. So hopefully you remember from organic chemistry when you would have carbon-carbon bonds and they had things that were attached to them, Newman projections was a way to look down that carbon-carbon bond axis and talk about what was the most favorable conformation, rotation about that carbon-carbon bond to allow for the most room with things. And so we talked about gauche versus anti and things like that to have the most stable conformation. That's ultimately what a Ramachandran plot is. A Ramachandran plot is basically looking at all the possible phi and psi angles, and we're not going to go through what those angles are, but those are just angles that we're going to have where we rotate about a carbon-carbon bond to give stuff as much room as possible. So you can imagine if we're doing certain rotations, that's going to allow some spaces to not be sterically favorable because atoms are going to be banging into one another, and then we'll click into a register where stuff has enough room. What that creates on this plot are what we call islands. So the islands, okay, which we see here, here, and to a lesser extent here, represent spaces where we have allowed steric conformations. So these islands are allowed steric conformations. Okay, so what this is going to then allow for is specific structural elements. We're going to get to the details in another video on this, but the two main secondary structural elements that we're going to talk about are alpha helices and then beta strands that interact to form beta sheets. But at the end of the day, what I want you to remember is that alpha helices are coils. And you can imagine if you were to make a coil, you would have a very specific geometry of the backbone on your charm bracelet to make a coil. And that's going to be a very different geometry than if you were to make what we call a zigzag, which is our beta strand. So what's represented on a Ramachandran plot, these are our beta strand allowed angles. So this is our beta strands. And then this is our alpha helices. Okay, so beta strands are our zigzags. So that's going to be a certain set of allowed phi and psi angles that allow you to live on this island where you're not having atoms bang into one another. Now, if you want to make a coil, you have to shift the kind of angle that you have. And so you're going to have a repeating angle that's in a different conformational space, but it's allowed because things aren't banging into one another. And at the end of the day, that's what a Ramachandran plot is. It shows us the allowed islands where we can either form zigzags, and let's put that on here. We're going to call beta strands zigzags, and we're going to call alpha helices coils. And you'll notice there's one little tiny island over here. And this little L tells us that that's for a left-handed alpha helix. So that's actually taking an alpha helix and winding it in the opposite direction. Well, you'd imagine to do that, you actually have to change the angles. So it lives in a different region of your conformational space. It's its own island in and of itself. Okay? So, big picture, if you want to form structure, you need to optimize sterics, so things can't bang into one another. That's our Ramachandran plot. And you need to optimize energetics. From an enthalpy and entropy standpoint, entropy is never going to be favorable to form a structure because you're freezing out molecular motion. So you need to compensate for it from an enthalpy standpoint, and we'll highlight how that works with the intermolecular forces that we have between atoms to stabilize these secondary structural elements that we're going to form, these beta strands and these alpha helices.